we only had to like avoid the contact between wheels and the rail. So no matter how little it was, a minimum lifting force lifting gap was ideal. And here you can see the bottom of our vehicle. There are 6 discs, 3 on each side, as you can see. And these discs actually are our levitation system. And in a minute, I'm going to be sharing the details of the system, but here you can see the positioning of the discs and how it works. So this is a model of our disc. As you can see, there are 48 slots on a disc, and this is an electromagnetic disc, we call it. In these 48 slots, we place neodymium N35 magnets, and we chose a hybrid system with cylinder and cubic magnets. So you can see there are 8 pieces of cylinder magnets and 40 pieces of cubic magnets. And the trick here is actually to arrange these magnets in a Halbach array arrangement. This way, the magnetic field is enhanced on the bottom side of the disc, and it's reduced on the top of the disc. And this effect has actually 2 benefits. So first of all, the enhancement of the bottom side like obviously causes a greater lifting force, and the reduction in the top side actually provides a protection for the sensitive electronical components on the top of the of the vehicle. And here you can see the measurements of our discs. So there are 6 of these discs, and each of them have a diameter of 19 centimeters and a thickness of 12 millimeters. And while designing these discs, we had to consider one thing too. So the working principle of this electrodynamic system is as follows. Like we arrange the magnets in a Halbach array on this disc, and we connect these discs to a BLDC motor, and we rotate the discs at very high speeds. So when we do this on the aluminum rail, because of the change in the magnetic field, eddy currents are induced, and this way the aluminum also acts like a magnet and repels against the magnets on the disc, and the pod is actually lifted. So we rotate these discs at very high speeds, such as 4,000 RPM. So the magnets repel to each other, and because of the high centripetal force, we needed a very durable disc to in order for the magnets to stay together and not fall apart. So when we designed this disc, we actually paid attention to the distances between the magnets, and the material of the disc was also very important. And for this, we chose cast polyamide, which is an engineering plastic and very durable. So the magnets can't break it, and the system is safe. So another aspect of our levitation system is the addition of a ferromagnetic sheet, so actually a steel sheet. The effect is it reflects the magnetic field on the top side of the disc to the bottom side of the disc. So with Halbach array, we already focused the magnetic field on the bottom side, but a little amount of magnetic field is still on the top side of the disc. So when we add a steel sheet, the electronic components on the top of the vehicle are completely secured, and actually it also has a positive effect on the lifting force, as you can see here in the graphs. Without the steel sheet, we obtained a lifting force of 108 newtons, and with addition of the ferromagnetic sheet, lifting force of 140 newtons was achieved. And on the right hand side, you can also see the flux lines of the magnetic field. Obviously, the bottom part, like in the right bottom picture, you can see that the magnetic flux lines are enhanced on the bottom side. And as I mentioned before, we rotate these disks with the help of BLDC motors. And here the challenge with the selection was that we needed powerful but lightweight motors, because we want to achieve a ideal lifting gap. So the vehicle should be relatively light. For this, we chose the anti-gravity series from T-Motors. It can easily reach to 400 RPM, 4,000 RPM, I'm sorry, and it can handle 5.8 Newton meters of torque, and it has a maximum power of 3 kilowatts. So this was ideal for our system, but in order to control this motor, we also needed an electronic speed controller. And for compatibility reasons, we chose the same company, but this time the Flame series of ESCs, and 80 amperes of an ESC with 80 amperes was ideal for our system. But there's a problem. So when we start the system, in the beginning, just when the disk starts to rotate, a torque value of like 13 newtons times meters was like met. But when the system comes to a balance, it's 3 Newton meters. And as you have seen in the previous slide, our motors can handle 3 Newton meters of torque. But the initial high torque values are just too much. So in order to come over this problem, we decided to use linear actuators. And the idea here is we start the vehicle on a height of on an initial height of 15 millimeters, and then we start the system. The disks rotate, and when it reaches the 4,000 RPM, we close the linear actuators, and the vehicle is landing on the magnetic field. And the wheels are not touching the ground, and a levitation height of 8 millimeters is achieved. So in total, the achievements of our levitation system is that it's safe and durable because of our durable and safe disk design. The high rotating speeds doesn't make a danger. And it also has an integrated PID control system. With sensors, we actually managed to control the stabilization of the discs. So in case the vehicle tilts to one way, the PID system controls it and brings the vehicle back to its balance. And we have met our goal of 8 millimeters lifting gap. And actually, we met a total lifting force of 822 newtons at the end of the developing progress, which is actually more than our initial goal. So we were more than successful in this manner. And here you can see a video of our levitation system from the last year in the competition. But I think there is a problem. I think there's a technical problem. I cannot open the video right now, or maybe I can. No, I can't. So I'm sorry for the technical difficulty, but right now I can't show you the video. So that was our levitation system. Thank you for listening.
So thank you, Hyperbee, for the wonderful presentation.